So I have an interesting problem for you. Okay, we have a triangular island, a roughly triangular island, and we have a surfer girl, right? She really likes surfing, and she's stranded, and she's only got her surfboard and a couple of materials, okay? And all this material is enough to build one hut where she can stay until she's rescued, hopefully. But under one constraint, okay? She wants to visit beach 1, beach 2, beach 3, at any of these points, just once, because you don't want to spend too much energy visiting them a bunch. She just wants to surf them once at least, you know. So, how can she do this without walking too much? Because she has to survive for as long as possible on as little food as possible. And walking means energy, and energy means, or spending energy means, you know, death. So what happens? What happens is at any point wherever she starts, if she wants to visit beach 1, she'll have to walk on a perpendicular line to this edge. And also another thing, this beach, and this beach, their lengths are all the same. That is, this triangle is equilateral. Okay? What does equilateral mean? Well, equilateral means, rather an equilateral polygon means polygon in which all side lengths are equal. Okay? So the laterals are equal. Okay, so now that we have that down, we're trying to figure out, okay, so she has enough materials to build only one hut, okay? But she has to visit all 3 of these, and the best way to do that is a perpendicular distance, like so, okay? Because, think about it, like if you went that distance and said, this is obviously longer than that one. So you want to take the shortest path to the beach. Okay. So she has to be conservative with her calories. She has to be conservative with her building materials. So she builds one and walks the shortest path. So if she built one right here, okay, so on day 1, she visits beach 1 and on a perpendicular. She returns. And let's denote that distance x. Okay. And on day 2, she visits beach 2 and returns. Okay. On day 3, she visits 3 and returns. This is y, this is z. Okay. So the problem is, where can she place her hut on this island such that she walks as little as possible? Okay, well, she'll walk as little as possible when these distances are small. Okay? And she'll walk cumulatively as little as possible if the sum of these distances are small. So what we're doing here is, essentially, we're trying to minimize the sum, x plus y plus z. Okay? And the variable that we have control over is the location of the hut. She can change the location of the hut as she pleases within the equilateral triangle. So, how can she visit all 3 of these beaches and still survive, and by only using the materials she has? Well, it turns out the answer is quite surprising. It doesn't actually matter where she builds her hut. Okay. Well, first, look at it like this. Let's see. Well, typically with an optimization thing, you wanna test some cases first, right? All right. So we start at the middle. Okay. Let's say she builds her hut at the middle. Okay. Now look at these lengths. They're all pretty moderately big. It doesn't seem too optimal. Okay. So we go to the far left, test this extreme case where she basically builds her hut on the corner So she can visit 2 and 3 just fine. They're right there, you know. But when she wants to visit 1, she'll have to walk all this distance and come back. So that doesn't seem too optimal either. Alright, so it's not an obvious problem. And that makes it all the more surprising that, in fact, it doesn't matter where she builds it. This sum right here is some constant. Right? And it turns out this constant is simply the height of the triangle right here. Alright? And this result comes from Viviani. This is called Viviani's theorem. Alright? So, what does Viviani have to say about our surfer girl and her island? Well, as we said before, it doesn't matter where she pulled her hut. The sum of the distances from that hut to the beach, drawn at these 90-degree angles, will be the same no matter what. This point, this point, this point, that point, wherever, it'll be the same. So that makes it very convenient. And in fact, this theorem is kind of profound, but it is deceivingly easy to prove. And I'll show you. So what does this theorem say formally? Well, it says that on a triangle, you have triangle ABC, pick some point P, okay? And the distance from point P to, say, AC, and distance from P to AB, and distance from P to BC, the sum of those distances is basically invariant. It's constant with respect to choice of the point, basically. So you can pick any point you like, and this sum will be the exact same. Okay. So how do we prove such a theorem? Well, here it goes. So we have our equilateral triangle, equilateral, and we pick a point, any point, right? And then we draw some helping lines from P to A, from P to B, and finally from P to C. Okay? And as before, we draw these distances. Okay? But we notice something here. This is a diagram we're all familiar with, I think. This is a triangle, right? And this line here is the height of the triangle. And we have a formula that consists of this length and this length. And it returns the area of the triangle. So let's say this is a triangle BPC, and the area of triangle BPC is what? It's simply let's denote this as H1. Okay. So this will be H2 and this will be H3. Right. So the area is simply BC times H1 over 2. Right? And similarly for triangle APC, let's see, triangle APC right here, we have a similar formula. Indeed, we have area of triangle APC is equal to AC times H2 over 2. And the exact same thing goes for triangle APB. And we'll have area of triangle APB is equal to AB times height 3 over 2. Alright. So we're trying to prove that an expression like this, the expression height 1 plus height 2 plus height 3, which is simply the sum of the distances. Here the distance is the height of the respective triangles, okay? We're trying to prove that this value is constant, okay, with respect to P, or choice of P. So usually with to prove something like this, you pick another point, right? An arbitrary point, right? And basically draw the exact same diagram. Okay? But here we're not going to do that because we have an easier proof, and me calculating these three areas kind of hints at it, right? So we have an H1 term here, H2 term here, and H3 term here. So why don't we go ahead and blindly add these things, okay? So let's add. Let's add those. Hopefully I still remember. So let's have triangle, the area of triangle APB plus area of triangle APC plus the area of triangle BPC, which should be equal to 1/2 AB times H3, as we said before, plus 1/2 AC times H2, as we said before, and 1/2 BC times H1. BC times H1, as we said before. Okay? And these correspond to that, this corresponds to that. And we can use the distributive law. Okay? We take out 1/2, so that becomes AB times height 3 plus AC times height 2 plus BC times height 1. Okay? Now, this is where the fact that this is indeed an equilateral triangle becomes important, because what do we have here? AB, that's the first side, AC, the next side, BC, the third side of the triangle. They're all equal to each other. These three are equal. Right? So we can call it, let's say, length S. Okay? So we replace the symbol with S to make it more clear to you what's going on. Okay? So we've simply rewritten our formula. And now look here, we can do the same thing as we did with 1/2. Simply pull out the S, and ta-da! What do we have inside here? H3 plus H2 plus H1. Alright? That's H1 plus H2 plus H3. The value we wanted. Right? But we've done really nothing more here than rewrite this, this addition of triangle areas. Right? We haven't really said much yet. But at this point it's really obvious that what is the addition of these three areas? It's simply the area of the entire triangle. This is just area of ABC. Alright? So it turns out that, okay, to summarize, our expression 1/2 S H1 plus H2 plus H3 is simply triangle ABC's area. Okay. But what do we know about the area of a triangle? Okay. We know that the area of the triangle does not depend on the point you pick. Right? Just because you decide to compute the area of the triangle using point P prime, let's say, and we split it into triangles from there, it wouldn't make any sense to have a different triangle area just because you computed using 3 different triangles. Alright? So what we're saying here is this thing here is a constant. Okay? With respect to choice of P. So therefore this thing here is a constant. And we know that 1/2 and S are constant. Okay? So if these were not constant, then this entire thing would not be constant. So this thing has to be constant with respect to the choice of P. And there you have it. H1 plus H2 plus H3. This expression is constant with respect to choice of point. Okay? So no matter what point you pick within the triangle, if you draw an H1, H2, and an H3, they all add to the same value. Okay? And this value, we can solve for this value, simply multiplying this, multiplying 2 to both sides, and dividing S from both sides. Okay? And this value is what? This value is the area of the triangle times 2 divided by the side length of that triangle. Now, we have to prove that this is equal to height H, which I'll draw as the height of the triangle. Okay? But this part's fairly simple, right? We can rewrite the area of ABC as simply okay, we put the 2 in the S front, and this we rewrite as 1/2 base times height. But again, what is the base of an equilateral triangle? Simply the length of any of these sides, because they're all equal. And we already denoted that as S. So we replace that with S. Okay? And look, it's this simple algebraic expression. These S's cancel out, these 2's cancel out. We're left with the height of the triangle. And that is the proof of Viviani's theorem. Right? Alright, so it seems natural to ask, well, what if the island she was stranded on wasn't perfectly triangular, or even equilateral for that matter? Okay, what if it were a quadrilateral island, like a rhombus or something? Okay, well, it turns out if it's not an equilateral polygon, I mean, you can make this island any shape you want, right? And obviously this property isn't going to hold. Okay, like say you pick a point here, you add the, this is a little difficult, but because formally you just extend this line and then you do the distance, but in real life you could simply take that path. But this is the shortest path to the extension of the beach. Okay, so, I mean, that right there, and then we could pick a point here, and it turns out this isn't going to necessarily be as easy to prove for any arbitrary polygon, quadrilateral or some such. So we stick with stuff that is easier to deal with, like equilateral polygons, and in this case, an equilateral quadrilateral. Okay, so let's say we pick a point. Let's make this a little bigger. Okay. Okay, it's a rhombus. And we pick a point. And as before, she wants to visit all the beaches. Okay. And in this case, there's 4 beaches. They're all the same length. She wants to visit them. And as before, she'll have to take the shortest path. So if she builds her hut right there, she's going to have to take that path, this path to 2, this path to 3, and this path to 4. Okay. Now we want to prove that x, y, z, and w, if you add them all up, it's constant, no matter where she builds her hut. Here, 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 here. Now, this was simple for equilateral triangles, and it turns out to be pretty simple for polygons of arbitrary order too. We basically do the exact same thing. Okay, take the point, draw the lines to the vertices. Okay, so we have a height 1, height 2, height 3, height 4. And we have the triangles. This triangle, this triangle, this triangle, and lastly, this triangle. And this proof is really similar to the last one. And you can imagine that we could do the exact same thing for an equilateral pentagon. Okay? Split it up into triangles. And this indeed does hold for an arbitrary number of vertices for an equilateral polygon. Okay. So yes, Viviani's theorem does extend. Okay. So let's write that down. But that's not what all of Viviani's theorem is. Viviani's theorem talks about the exact value for the sum, and this turned out to be height, h, the altitude of the triangle. And we have actually a similar thing for polygons, okay? So we start with a pentagon, okay? And we pick a point P, okay, a precise point P. This is in fact the center of the pentagon, such that its distances from the center to the vertices are all the same. Okay. So it turns out that, well, first of all, we can label these, and it's easily seen by side, side, side that all of these triangles are congruent to each other. Okay. So this triangle is congruent to that one, this triangle is congruent to that one, because they all have the exact same side lengths. So we know that they all have the exact same altitude also. Okay. Okay, so we can label that common number h. Okay. This is what is called the apothem of a polygon. It's where you take the center and draw a distance to the opposite side. Okay. Draw a distance to any arbitrary side, because since it is the center, it'll be the same as we showed. Okay. It turns out that this value, the sum of the heights, okay, I'll denote it like that, is simply equal to n times the apothem. Okay. And this comes easily because we do the same exact thing. We add up the areas of the triangles. Let's denote side length s. And since we know it's an equilateral pentagon, we say sum of s hi over 2, where we're summing over all of the 5 triangles. Okay. But what can we do about this? Since s is a constant, 2 is a constant, we can distribute it out of the sum like we did before. Remember when we did sh1 plus sh2 plus sh3, we simply, 2, pulled out the s, pulled out the 2, and we had an expression like this. Okay, we're essentially doing the same thing here, except with an arbitrary number of vertices. Because here we had a triangle, here we have a pentagon, but we're trying to generalize to n-gons. Okay? So we can do the same exact thing. We pull out and we have this, the sum of the distances as we need, okay, over the n triangles, okay. But what do we know about the area of the triangles? Okay, the area of the triangles is simply 5 times, well, n times n times side times height over 2. Okay? Why is this so? Where did I get this? Well, we pull out a single triangle from there. We have a height, or aperture h. We have a length s. And by the area formula, we have base times height over 2. Okay? And we simply take this and add it n times. Okay? Since these triangles are congruent, we can, this is just a multiplication, it's a duplication n times of a congruent triangle around the polygon. So this area is equal to that. Okay? Alright, so this is equal to s over 2 that. Okay, now we can cancel out s over 2, and we're done. N times h is equal to the sum of the distances. Alright, so it turns out that Viviani's theorem generalizes pretty strongly to equilateral n gons, not just 3 gons. Okay, so we want to do something a little weird here. I mean, we've been picking our huts so far within the polygons, right? This makes sense, you know. I take the distance, you know, this line will be pretty easy to draw. But we can technically draw them outside of the polygon, right? Suppose our surfer wants to build a little raft hut. You know, maybe she accrued enough materials for that, and she still wants to visit all of these beaches. But what about this one, right? There's no real perpendicular to it, so our analogy kind of breaks down. So what we do in geometry is we kind of extend this beach, and instead of going to the beach, we go to the beach line and take the shortest path. Okay. All right. And then we take this line right here. Like that. Same thing here. Draw the perpendicular to the beach line. Draw this one normally. Alright, now but how do we take the sum of these distances, right? I mean, obviously if we put a point way up here and drew all of these distances, the sum is going to be way larger than h. And if it's not, we can still make it yet bigger, you know. We have infinite space in the ocean to place our huts, such that this theorem, Viviani's theorem, is not going to hold. So it turns out this problem can be fixed by simply defining our distance differently. Okay. First off, let's start off with a simpler figure. Okay. For illustration, I'll start off with a square. Okay. And she wants to build a hut right there, on the raft, on a little floating raft. Okay. And as before, this time we're gonna start off with the proof structure. We're gonna draw the lines to the vertices and construct these triangles. All right. We construct these triangles. Now, this isn't familiar to what we've drawn before, where we had something like this. Okay. That was familiar. Okay, we have 4 triangles adding up to a constant area. No matter where you place the dot, no matter how you divide up the triangles, okay, Now, the flaw that is introduced in our extension here is that we can place this point anywhere and make these triangles as big as we want, and it's not necessarily going to be a constant area, obviously. If we place it here, this huge figure here obviously has a different area than this square, or even this figure. So you don't expect this theorem to hold for points outside of the polygon. Yet we can make it simply by defining our distances differently. But first, let's do this. Let's add up the areas. Okay. Okay, let's denote this. Hold on. Okay, let's extend this line here. Okay, we draw our height, and let's extend. I'm going to color the heights a different color for clarity. Okay, and another height here, and another height here, or rather a distance. Another one here. What else do we need? Ah yes, this one here. And another one here. Okay. Alright. And what I'm going to do is a little strange, but it's not different from what we did before. Essentially, we still have 4 triangles. We have the first triangle right over here. Okay. Go into this edge. We have our second triangle right over here. Okay. And we have our third triangle right over here. Okay. Okay. Where's our fourth triangle? Our fourth triangle should consist of this edge and the 2 lines going to the endpoints of that edge. So, yes, the fourth triangle is right here. That's our fourth triangle. But you see that this fourth triangle lies entirely outside of our polygon. Okay. So, what's the constant value here? We can actually find the constant. It turns out this constant is this, right? The area of the square. No matter where you put the point, the area of the square stays the same. But now we're going to express this area in terms of the sum of our triangles like before, just blindly. We don't really know what we're doing yet, but we're going to find an expression that represents our constant area in terms of our formulation here. Okay? We're just gonna do it and see what we get. Okay, so let's say K, which represents the area of just a square. So let's say K square. Okay. K square is equal to well, let's see. This is a typical area addition subtraction problem now. Okay, let's say, so basically we have this triangle here. Okay, we have this triangle here. Okay, add up that triangle, and then we add up, okay, we add up this triangle here, and then we add up this triangle here. So we add up triangles 1, 2, and 3. But we have all this extra space, so what do? We simply subtract triangle 4. Boom. Alright? That's pretty clean. So what we have is triangle 1, triangle 2, triangle 3, minus triangle 4. Alright? But we did get the heights of these triangles, which again is simply the distance from the beach line to the hut, or to the hut to the beach line, to the shortest distance, which is perpendicular. And perpendicular means what? Altitude. And altitude means what? Height. So let's say that's the height. Height 1, okay. And this is our height 2. And this third triangle has height 3. And this fourth triangle has height 4. Okay? We're talking about just this part right here. That's height 4. Right? So, as we know from the triangle area formula, k equals base times height over 2. Right? This is pretty simple now. We denote the equilaterals side length as s. Okay? And every triangle has side length s. Okay? They have a base s because that's how we constructed these triangles. Remember, we drew lines from the raft to the ends of the vertices of each of the 4 sides. So each of them are going to have an s. So we should expect each of them to have an s somewhere in the equation. So k1, that becomes s times height 1 over 2. K2, that becomes s times height 2 over 2. K3, that becomes s times height 3 over 2 minus K4, that's s times height 4 over 2. Alright, and as before, we distribute out the s over 2 and get h1 plus h3, h1 plus h2 plus h3 minus h4. Alright? So that is our area. Okay? And as before, what did we say? We said this area is constant with respect to the choice of point. Okay? No matter what point we choose, we can still do this construction. Right? We can still do this construction, and we'll still have this equation, but the area still stays the same. And since this is a constant, this has to be a constant. Alright? So this is similar to what we had before, except we have these minus signs. Alright? Still, we want to be able to say that the sum of the distances are the same. But if we say that, we no longer define the distance as we normally do, which is simply the length of these lines. Because obviously that's not going to be true if we define that as distance. As we showed before, if we pick a point here, the length of these lines and you sum them up, no, obviously they're not going to be the same. They're not going to be constant, you know. You could widely vary it, infinitely, you know, many number of variations. But we simply, we pay attention to this negative sign right here, okay? This hints at what you want to define another distance as, okay? And we'll call this this is not much of a distance as it is like a vector, okay? But for here, we'll just call it a distance, okay? So we define distance as when apparently this h4 has a negative distance, right? And if we say h4 has a negative distance, then we can say the sum of the distances is constant. Do you see what I'm saying? Basically, we redefine distance to include negatives, or what I'll call signed distance. Okay? Signed distance. Take note of that. Signed distance, where in the definition of the distance you can include negatives. So, I'll rewrite this for clarity. This is h1 plus h2 plus h3 plus negative h4, right? Now, we don't normally regard this as a distance, but if we do regard it as distance, we can say distance plus distance plus distance plus another distance is constant. And Viviani's theorem holds still, linguistically. Okay? So that's our suggested extension. Okay? And to clarify this, to be more precise, when we have a point outside of the polygon, when we approach an edge from the outside, okay, this is a negative distance. Okay, this right here H4 has a negative distance. Okay. H2, well, I'll try to explain it better in a different diagram. Okay. See, this is a kind of a subtle point. It's maybe a little hard to grasp, but it's really not too difficult. Okay, let's start with our familiar equilateral island. Okay. When we have a normal point here, we have positive distances. We never even worried about negative distances, so they were positive. So it makes sense to still include the definition of our original distance. Basically, whenever you have a point inside, it'll be positive. Okay. Now, when we extend it to the outside, right, we take this point, move it outside, right? Now we're going to have this sort of line right here. And we're going to make that a negative distance. Okay? But we still approach this line from the same side, basically. So this is still a positive distance. Okay? And this is also still a positive distance. Okay? So Viviani's theorem extends, in a sense, to a sine distance. Right? So we'll write the sum of the signed distances is constant. Alright? Okay? And as before, it's still equal to this value, which is either the height for triangles and the apothem for any other polygons. Okay. So essentially, what we're saying here is if we have a suppose this is some part of a larger polygon. If we approach this line from the inside and we say that's positive, whatever you define the inside to be, then if you approach it from the opposite side, that distance must be negative. That's really all there is to it. So you're defining a negative as an opposite of a positive. All right? And if you define it like so, then the theorem will in fact hold. So as we showed before, right? Draw an equilateral polygon. Okay. Take a point out there. Draw our triangles. Okay. And this is our negative height right here. And this should have a positive height. Because if you were to draw it from the interior into that height, you're approaching it from the same side. You're approaching this line from the same side as you would from the interior. Okay? You would approach it this way, so this height is also positive. And you would also approach it from the interior, this height's positive, and this height's positive. Okay. And then we simply add up the areas. We simply add up the areas as before. We go A1, so we'll call it S. Okay, S H1 over 2, SH2 over 2, SH3 over 3, SH. In fact, this isn't even necessarily have to be a pentagon. This can be any n-gon. So over 2. Has to equal K, right? And now, since we expanded the definition, these heights don't necessarily have to be positive. Okay. So we distribute out to S over 2 as before, and get this. And this shows that this is constant. Okay. So that's really all there is to it. We've been working with only equilateral polygons, like the equilateral pentagon, or the rhombus, or square, rather. But yeah, so the rhombus is an equilateral polygon. In my previous example, it did look like a square, but the same holds for the rhombus also, because the rhombus is an equilateral polygon. In equilaterals, the square is a regular polygon because it is also equal angular. Okay, as I defined in the beginning, if it's both equilateral and equal angular, it is regular, right? Okay, so let me write that. Okay. Regular is basically equilateral and equiangular. Okay. Okay, so we talked about these polygons. Okay. But we haven't talked about these polygons. Okay. Now if we talk about equilateral polygons and say Viviani holds for equilateral polygons, since regular polygons are equilateral, okay, since they're both equilateral and equiangular, they must also be equilateral. So in fact, what we have is regular polygons equilateral and equiangular. Hold on, I drew that wrong. Okay, these are just polygons, just a set of polygons, and this right here is the regular polygons. This small intersection right there. Okay, so it turns out all regular polygons are also equilateral, right? So we've covered all the regular polygons simply by covering all the equilateral polygons. Okay. So the only thing we've yet to cover is this part right here, the equiangular polygons. So we're going to do that because it seems natural to ask, okay, if our surfer girl, right, why does she have to be on simply an equilateral triangle? Okay, why can't she be on an equiangular triangle? Well, in the three-gon case, in the triangle case, these are exactly the same thing. It turns out that the triangle is simple enough that equiangular implies equilateral. So there's no such thing as just a strictly equilateral triangle. Equilateral and equiangular are exchangeable when it comes to triangles. So we'll extend it. We'll go a little bit further. Okay. Remember our quadrilateral case. She was on a rhombus island. Okay. So how about this time? Okay, since we covered the equilateral case, this time she's on an equiangular quadrilateral that is not necessarily equilateral. So the simplest example of such a polygon is the rectangle, which is the equiangular fourgon. Okay. Now, these two sides are not necessarily equal, right? Meaning that our previous method of proof, whereby we drew the point, we drew the triangles, by splitting through lines from the point to the vertices, this method won't work. Because what did we rely on? We relied on the fact that all of these sides were S, and thus all of the triangles had area formulas resembling this form, where this is the variable and this was just the constant, and we added them up to n terms, okay, from I equals 1. And we sum them up to get, SH1, 2, SH2, 2, all the way up to some n. And when we factor the s over 2 out, like so, and then we ended up with the expression we wanted on the inside, which is the sum of the distances. But we can't do that here. Why? Because these S2s are also going to need to be indexed, because they are not necessarily going to be equal. Say if this is S1 and S2, these are not necessarily going to be equal, so that's not necessarily going to be able to be distributed out like that. Okay? So this is not necessarily going to be equal to that, so this method won't work for all equal angular polygons. But there is, thankfully, a method that is known to work, and I will show you that right now. Alright. And this method is a little more complex. You start off with the equiangular polygon. Draw it a little big. Okay. Equiangular. And this time, you draw a regular polygon within it. Now, you want this to be oriented in such a way that the corresponding sides are parallel. Okay? Okay. So, what is the equilateral and equiangular, that is regular quadrilateral? That it would be a square. Okay? So you have a square within a rectangle, and since these two lines are parallel, the distance between them, no matter where you put that distance, it's going to be the same length. Okay? And the same goes for here. Every single length that you draw, every single distance that you draw between the two lines, there's a unique measure. Okay? This is how you define the distance between two parallel lines, actually. This is why you can do it. Because no matter where you do it, this measures uniquely the same thing. So no matter where you draw this line, it seems pretty intuitive that indeed the distance will be the same at every single point, as long as these two lines are parallel. Okay? Alright. Okay, so we aren't officially done, but we're very nearly there. Okay. So what I just proved was, for a point lying like somewhere in there, okay, we can confidently say that the sum of this, and this, where these are the distances from this vertex to the edge of the equiangular polygon, is a constant with respect to choice of this vertex. Okay? Now it's pretty clear that this argument is limited because we don't have to choose a point from there. No? We can choose a point on the exterior. Okay? But this argument that I used before is still, you can actually extend that for points on the outside. Okay? So let's label it C1, C2, C3, C4. Alright. Okay. And label the distances to the beaches. H1, that'll be H2, and that'll be H3, and this tiny bit will be H4. Okay? So what we did was basically we added these up, right? When it was in here, they were all positive values. But now that may no longer be the case. In fact, since we moved it left here onto the left of this side, this value, H4, becomes negative. Okay? But the argument we used previously was that this was constant. This is constant. So the sum of these are constant. So this, which forms the length from this vertex to the edge of the equiangulator polygon, which is a rectangle, is x1. And the sum of the subsequent distances is therefore also constant with respect to choice of vertex. But this argument doesn't change when you move it to the left. Suppose we choose a vertex on the left of this, so this sign must be negative. That is, H4 is on the left of this edge, so it's a negative sign, a negatively signed distance. But still, look, C4 minus H4, or rather C4 plus the negatively signed H4, it's this edge right here. Is this line segment right here. We color that in. Right over here. Okay, we can shift that up to right there, and it becomes clear that that again is still the distance from this vertex to that edge, right? And the others are still the same. Okay, x1 is that. This is x1. Still. And this is x2. Move it up. Then add it together. And then this is still x3. Take that, move it, add it to that. So again, we still have x1, x2, x3, x4, and those are the line segments connecting the vertex to the opposite, to the corresponding edge, in a perpendicular fashion, of course, like so. So yes, they are indeed distances to the beach from the vertex. So whether or not you choose a vertex from here, choose a vertex from here, you're gonna this method's still gonna hold. Okay. So this method still holds no matter what. And so we conclude that yes, Viviani's theorem, first part, which was that, which I'll just split it up into two parts. Let's just say that the first part says for interior of, for a point in the interior of a triangle, an equilateral triangle, the distance from that point, the sum of the distances from that point to the sides is constant with respect to choice. Okay. Now what we did here is we took this, extended it to an n-sided polygon, equilateral. And we were able to kind of extend the second part too. And we were able to say that this constant indeed equaled n times t. Okay. So n times h, or h was the apothem. Okay. But with the equiangular one, we extended it further. Equiangular